Okay, we will start our lecture on torsion. Basically, in reinforced concrete members, this is also subjected to additional factors, that is called torsion, in combination with bending moment and shear. Let us see what is the torsion and how it is developed in a reinforced concrete structures. Okay, we will see with an example. Let us see the first example. First example is an example of canopy. Here number B, it is shown a fixed end with curved beams. Okay, fixed and curved beams. Third one with some grid structures, and the fourth one shown here is the frame structures. Okay, let us see in these 4 examples how the torsion is developing. Okay, we will go details slowly. So, before that let us see what. Okay, so what happened to the first structures if we look at this. Okay, in canopy beam is introduced for maintaining equilibrium of moment in the cantilever slab at the junction of the beam. What I am trying to say is that the torsion in canopy beam is induced for maintaining equilibrium of moment in the cantilever slab at the junction of the beam. Basically, it is talking about in this location, the torsion will basically maintain the equilibrium of these structures. Okay. Torsion in a curved beam is introduced because the center of gravity of all the loads and reaction, CG of all the loads and reaction of this curved beam is on one side of a section of the beam, which does not lie mainly on the axis of this beam. This is the axis of the beam, it is not lying. Okay, if you take the CG of the shear and the moments. Okay. In grid, what happen? The flexile rotation, basically in this part the rotation will occur because of the loading here. Okay, because of the loading here. I'll show you another pictures where you will get the more details on that. Because of the loading here, or because of the loading here, a rotation will occur, or even in this portion of the beam, because of the loading here there will be rotation, or because of the loading here there will be rotations. Okay, so that rotation will give you the torsional moments. Okay. Similarly, if you see the last one, that is the frame structures, because of the loading here some kind of torsional moment, or because of loading say somewhere in between that or anywhere here some kind of torsional moment will develop while generating or while calculating this beam. We have to consider the torsional moments. Okay. Now, see little bit details on that. Okay. Okay. Before that, let me tell you that there are 2 types of torsion and moments are there. Basically, one is called statically determinate or equilibrium torsion, or some of the books you will find it is called as primary torsion. Okay, primary or equilibrium torsion, or you can say statically determined. Okay, maybe you can see here, this is called primary or equilibrium torsion in beam. Okay, and this is called secondary or cantilever torsion. Now, if you see, just look at the previous examples that I have shown here, this one. Okay, so because of the load here, what will happen in this part, there will be some kind of movements. Okay, so this torsion, this because some movement is developing, so this is trying to keep these structures in equilibrium. Okay, so this is the torsional moment. Okay, similar to if you look at this, though 2 supports are there, but because of some load here in this part is developing some movement, so a torsional, the twisting movement is developing here, which is trying to keep these structures in equilibrium. Okay, so these are basically indeterminate kind of things. Okay, more detail, we are not dealing with the more details on this. Maybe some structural analysis courses you will find details on this, or if you are interested you can refer some kind of mechanics books or structural analysis books, you will get details on that. Okay, so this type of torsion is called basically the secondary or compatibility torsion. Okay, or sometimes it is called indeterminate torsion also, because they are statically indeterminate. So, indeterminate structures, though it is indeterminate, but still you can find out there are some methods are there, you can go through. Okay. Now see more details on this. The first one, whatever I have shown, the canopy kind of things. Okay, so here this is a cantilevered shell roof for canopy kind of things. So here the load will be there, right? So because of this load, there will be moments. Okay, additional moments are there. So this moment, counteracting moments, is basically the torsion. Here it is shown. Okay, so this is a beam subjected to equilibrium torsion. Okay. So this is a beam basically supporting a lateral overhang. That's what I have shown in the first examples that you can see in this one. So similar things, basically this one. Okay, this one is nothing but here this one, and this is the one. Okay, so this is basically called a primary or equilibrium torsion. Okay, so in this torsion there will be moments, that is called the twisting moments. Okay, so twisting moments are coming. I am sure in mechanics you might have gone through all these parts, what is twisting moment and how they come in the pictures. Okay, how what is the moment diagram of the twisting moments, that also been given in your mechanics classes. Okay, I am not dealing much. Okay, now let us see for this type of, or suppose for this type of, for this type of case, what happened. Okay, let us see this in a, okay, if you see this beam, this is the main beam. Okay, ABC, say ABC beam, and this is another beam BD. So these are monolithic structures. Okay, now what you can see that because of this load here, okay, there will be rotation, and this part some rotations is there. So if this part is rotating, so this part is little bit rotating. Okay, so what happened in this part, because of this rotation, a twisting moment will develop at the beam ABC at B, right, and at the end of B in this part, for this member BD, there will be a bending moments. Okay, now the magnitude of this twisting moment will depend on the torsional stiffness of member ABC as well as the flexural stiffness of member BD. Okay, so these are basically statically indeterminate. Okay, so we can find out this value using the indeterminate structure analysis. Okay, so that's why this type of these torsions are called the secondary torsions, right? Okay, we'll go to the next. So these are again, if we look at this part, some of the examples of this secondary torsion and primary torsions are shown here. Okay, same things I have already discussed earlier. So more details I am not discussing here. We will go to the next part. What our, see, one more thing, let me tell you that a torsion will not develop individually. It will develop either with shear or with the bending moment. So we will see next how, what are the defined guidelines given in the code book to deal with this torsional moments. Okay, so come to the code book's guideline. If we refer to the code book, then in code book IS 456 2000, that is basically in clause number 41, this is given the limit state of collapse. Basically it has talked about the details design using the torsion. Okay, then if you go this clause number 41.2, it is said that the sections critical, basically it is talking about what is the critical section for torsion. The sections located less than a distance d from the face of the support may be designed for the same torsion as computed at a distance d, where d is the effective depth. Okay, so it is talking about that you find out the torsion at a distance of d from the face of the support, and the same value you can take when the distance is less than d. Okay, now we will see next clause, that is clause number 41.3. In clause number 41.3, it is talk about shear and torsion. Okay, when torsion is there in addition to the shear, then how to deal with that. Okay, it is said in clause number 41, if you read clause number 41.3.1, it is talking about equivalent shear. Equivalent shear. Okay, how to deal with this equivalent shear? It is said in this that equivalent shear BE is equal to BU plus 1.6 TU divided by B. What is this BE? BE is the equivalent shear. Okay, equivalent shear means including the torsion. BU is the shear. That shear, what generally whatever the critical shear or shear we consider. TU is the torsional moment. So you have to calculate the torsional moment TU, and B is the breadth of the beam. Okay. So codebook guideline is that whenever a section is having torsional moment in addition to the shear, then we have to calculate the equivalent shear using this equation. Okay, I am not going to derive this equation. Those who are more interested, you can refer any kind of this RCC books, you will get the details on this. Okay, so just some as quickly as possible we are trying to cover this course, so I am not going to derive it. Okay, so in this case, what is this B? B, I told that it is the equivalent shear. This equivalent, then once we know this, then we can calculate the equivalent nominal shear stress. So if you remember that earlier we have calculated the nominal shear stress, what was that? That was BU divided by BD. So here it will be BE divided by BD. Okay, so this will give you the equivalent nominal shear stress. Okay, and this value shall not exceed the maximum shear stress, that is tau C max in any case. Okay, that we have discussed earlier. Table number 20, if you refer the closed code book IS 456-2000, for different grade of the concrete there is a maximum limiting value of shear stress, design shear stress. Okay, so it cannot exceed this. Now once we know this value, then this tau BE we need to compare with design shear stress tau C. You remember that given in table number 19, that is in as per the clause number, you can refer the clause number. Table number 19 is probably given in page number 73. If I just go back, that is in clause number 40.4. Okay, so you have to compare once again with this tau BE and tau C. Okay, whenever tau BE is more than tau C, we have to go for design of shear reinforcements. Okay, otherwise what we have to do, we have to provide the minimum shear reinforcement. Okay, right, that means what I am trying to say is that whenever this tau BE is less than tau C, provide minimum shear reinforcement. Okay, as per the clause number 26.5.1.6. Okay, what is written in clause number 26. I will just copy that part. Or if tau B is greater than tau. Now see, there are two conditions may arise. One is when tau B is maybe less than tau C. Another case may be tau B is more than tau C. In case of tau B less than tau C, we have to refer the clause 26.5.16, and according to this guidelines, this is the guidelines that I have written, we have to provide the minimum shear reinforcement. When tau B is greater than tau C, we have to provide transverse reinforcement as well as the longitudinal reinforcement also. And how to provide that? That guidelines is given in clause number 41.4 of IS 456-2000. Okay, so what is those guidelines? Let us see now. Let us go to clause number 41.4. If you go to clause number 41.4, it is talking about the longitudinal reinforcement first. Longitudinal reinforcement in members subject to torsion. Okay, so first it is talking about in clause number 41.4.2. Okay, what are those things? It is talking about the longitudinal reinforcement. Longitudinal reinforcement. Now, how to give the longitudinal reinforcement? Let us see that. It is said that the longitudinal reinforcement shall be designed to resist an equivalent bending moment mu1. Equivalent bending moment mu1, which is equal to mu plus mt. Okay, this is equal to mu plus mt. Now, what is this mu? Mu is the bending moment at the cross section, that is your normal bending moment because of the normal loading, whether it is a UDL or point load or whatsoever it is. Okay. Now, what is this mt? Mt is the torsional moment. Okay, basically it is calculated like that. This mt is calculated using this equation. Mt is equal to Tu into 1 plus d by b divided by 1.7. Okay, this mt is calculated as mt equal to Tu into 1 plus d by b divided by 1.7. Here Tu is the torsional moment. Okay, d is the overall depth of the beam and b is the breadth of the beam. Okay. Now, again there is a condition given in clause number 41.4.2.1. What is the condition given? It is said that if the numerical value of mt, exceeds the numerical value of mu, moment mu. So, it is saying that numerical we do not go for sign. If the mt is greater than mu, longitudinal reinforcement shall be provided on flexile compression phase in addition to the tension phase. What it is saying that if mt is greater than mu, you have to provide the compression reinforcement also. Okay, basically phase such that the beam can also withstand an equivalent moment me2. For which moment? That is for this moment, for me2 is equal to mt minus mu. It is similar to, you can say, your earlier case also, whatever we have discussed in case of plane without considering the torsional moment, that if the mu design moment is more than mu limit, then we calculate m2 and we provide compression reinforcement. Here also the similar thing it is talking about, that when this mt is greater than mu, then we have to calculate the moment, that is mt minus mu, and for this moment we have to provide the compression reinforcement. Okay, and it is basically assumed that it is acting as an opposite sense of the moment mu. Okay, anyway, so we have to provide reinforcement on both phase. Okay, when we have. So, and then we know already we have discussed earlier how to use the equation, different equations for calculating of the moment. Okay, so thing is that we need to calculate, we need to know how to do this calculation part. Okay, so first of all that we are calculating this me1. Okay, for this me1 we have to calculate the reinforcement. Then in me1 there are two components, there is mu and mt. What is that mt? Mt is basically because of the torsional moment, so that mt we have calculated. Now, if you see that mt is greater than mu, then we have to provide the torsional this reinforcement on the torsional reinforcement on the compression side also. So, this is about the longitudinal reinforcement. Next, we will see the transverse reinforcement, how to provide the transverse reinforcement because of the torsion. Okay, come to the next slide. Next slide, that is next clause is given in 41.4.3. In 41.4.3 it is talked about transverse reinforcement. Okay, so transverse reinforcement. Okay, it is said that two-legged closed hoops enclosing the corner longitudinal bars shall have an area of cross section ASB given by. Okay, it is saying that two-legged transverse reinforcement we have to give. Okay, at least. Okay, so this ASB will be equal to, this is the area of the transverse reinforcement. It is to be given like that, TU SB divided by B1 D1 into 0.87 FY plus BU SB divided by 2.5 D1 into 0.87 Fy. okay, but the total transverse reinforcement shall not be less than, that means what it is saying, that this ASB cannot be less than tau B minus tau C multiplied by BSB, B into SB divided by 0.87 Fy. Okay, so this is the conditions given in the code book. Now let us see this, what exactly it is saying. What is this meaning of the symbol? First of all, Tu already we know that it is the torsional moment, Bu is the normal shear force, okay, SB is the spacing of the stirrups reinforcement. Whatever the reinforcements we are providing in the transverse reinforcement, what is the spacing between that we have to know. B1 is the center to center distance between corner bars in the direction of the width. Okay, let us see what is that B1. Okay, so if I draw a beam here, let us say this is a beam. Okay, so in this beam, say we are in this beam we are using some torsional reinforcement. So this is the reinforcement, say here we have provided reinforcement and then we are providing this transverse reinforcement like that. Okay, don't worry about this shape. Okay, now what is this B1? Is B1 here is the this from this center to this center distance. Got it? This is called as B1 here. Next, D already we know. Okay, that's I need not to write. Then D1 is this one. This is the D1. Okay, so the meaning is written. B1 is the center to center distance between the corner bars in the direction of the width. So it is in the direction of the width. D1 is the center to center distance between the corner bars in the longitudinal direction, other directions. Okay, B is the breadth of the beam, that is this B is the from corner to edge, basically this edge to edge is the B. Fy we know what is the tau B is the equivalent shear stress that we have calculated earlier, and tau C is the shear strength of the concrete as per table 19. Okay, so see in this equation one of the things we have to assume, we cannot calculate 2 because I have 2 unknowns but I have one equation. So what I have to either ASB or SB we have to calculate. Generally what we do, we assume ASB with some diameter, specific diameter we assume ASB, and from there we used to calculate the spacing and then we check whether the spacing is within the limit or not. Okay, if it is within the limit then we can say our design is safe. It is beyond the limit, then we used to redesign it, or redesign it. Here redesign means we have to change the diameter of the bar. Okay, so this is how we can do the design of reinforcement for torsion. Now in addition to the above whatever we have discussed, there are some specific conditions are given which are to be satisfied by the reinforcement. That is what it is written: beam subjected to bending moment, shear and torsion moment should satisfy the following requirements. First of all, when we have tension reinforcement, where we are providing only tension reinforcement, those tension reinforcement we have to check that it is satisfying the minimum reinforcement criteria. What are that criteria? AS by BD equal to 0.85 Fy, and you have to check that whatever the tension reinforcement we are providing here, that is satisfying the minimum reinforcement criteria, as well as we have to check the maximum tension reinforcement criteria, and what is that? That should not be more than 4% of the cross section area, that is 0.04 BD. Fine. So this is one information that we have to check. Then we have to check the compression reinforcement. Okay, because here we are also, if MT is more than MU, we are providing compression reinforcement, so you have to check that it is satisfying the criteria. What is that criteria? That maximum value shall not exceed 0.04% of the cross section area. Then in addition to that, we have to provide side face reinforcement when the depth is more than 750 mm. Okay, so a beam exceeding the depth of 750 mm and subjected to bending moment and shear shall have side face reinforcement because depth is very high. However, if the beams are having torsion moment also, the side face reinforcement shall be provided for the overall depth exceeding 450 mm. Okay, so in case of torsion moments, we have to provide the side face reinforcement when the depth is more than 450 mm. The total area of side face reinforcement shall be at least 0.1% of the wave area and shall be distributed equally on two faces at a spacing not exceeding 300 mm or wave thickness, whichever is less. What it is saying that the total area of side face reinforcement shall be at least 0.1% of the wave area. Okay, and it shall be distributed equally on both faces at a spacing not exceeding 300 mm or wave thickness, whichever is less. Okay, so this is another guidelines that we have to keep in mind when we have a normal beam. In case of normal beam, if the depth is increasing 750 mm, in case of a torsional beam with torsion reinforcement, then when it is exceeding 450 mm. Okay, next guidelines, what is there? Transverse reinforcement. Okay, the transverse reinforcement shall be placed around the outermost tension and compression bars. They should pass around the longitudinal bars located close to the outer face of the flange in T and L beam. Okay, so transverse reinforcement shall be means it is talking saying that it should be just outside the outermost tension reinforcement. Means it is talking about that if we have tension reinforcement here, compression reinforcement here, tension reinforcement, exactly from the outside we have to provide the torsion bars. Okay, maximum spacing of shear reinforcement. The center to center spacing of shear reinforcement shall not be more than 0.75 D for vertical stirrups and D for inclined stirrups at 45 degree. Okay, while discussing the shear I have discussed this, but it should not exceed 300 mm, whichever. Okay, so in any case it cannot exceed 300. So out of these two, whichever is minimum, that means what I am trying to say that for vertical stirrups it should be 0.75 D or 300 mm, whichever is minimum, and for inclined stirrups it will be inclined stirrups at 45 degree, it should be D or 300 mm, whichever is minimum. Next, shear reinforcement. Shear reinforcement, minimum shear reinforcement I already told you. Okay, as per the clause number 26.5.1.6 that you have to provide. Okay, now said how to distribute the torsion reinforcement. The transverse reinforcement shall consist of rectangular closed stirrups placed perpendicular to the axis of the member. That we know that it is to be perpendicular to the axis of the member. The spacing of stirrups shall not be more than the least of x1 or x1 plus y1 by 4 or 300 mm. Where x1 and y1, what are those x1 and y1? Let me just show you in a figure quickly. Okay, suppose I have a beam like that. So what is the x1? x1 is basically it is talking about from the center to center distance of the reinforcement. Okay, so what I have to do, I have to place some reinforcement here. So these are the main reinforcement I am providing here. Okay, it is a round shape basically. Okay, main reinforcement is to be provided in a round shape. Say, okay, so these are the main reinforcement I have provided. So what you do from the center of the main reinforcement to the center of the main reinforcement here, this is called y1. This is denoted by y1. Okay, and then from the center of this to the center of this gap is denoted by x1. Okay, so it is saying that the spacing of stirrups shall not be more than least of x1 or x1 plus y1 by 4 or 300 mm, where x1 and y1 are as shown in the figure. Okay, next part, the reinforcement in flanges of T and L beam. Whenever we are talking about the T beam and L beam and the flange, how to provide the reinforcement. For flanges in tension, a part of the main tension reinforcement shall be distributed over the effective flange width or a width equal to 1/10 of the span, whichever is smaller. For effective flange width greater than 1/10 of the span, the nominal longitudinal reinforcement shall be provided to the outer portion of the flange. Okay. So, in case of T beam and L beam, we have to provide the reinforcement as per these provisions. Okay. So, these are certain provisions that is given in addition to the design, and that we have to keep in mind while designing the torsion reinforcement. We will quickly take one example and we will see how we provide the torsion reinforcement, or whatever we have discussed, how to provide them. Okay. Okay. Now, we will take an example. Let us say we have a rectangular beam of breadth 400 and depth 700. Okay. Let me start with this drawing itself from beginning. Okay. So, let us say this is my beam. This beam has a overall depth and as well as we have some breadth. Okay. Some reinforcement will be there, no doubt. So, let us say the effective depth also I am showing the beginning itself. Okay. Let us what is given, that just the overall depth D is equal to overall depth, this D is equal to 700. Okay. So, the overall depth is given as 700. Then what is known to us? This depth is known to us. This depth is say given as 650. Okay. Small d is equal. So, effective cover is 50, and say that B is given as 400 mm. Say in this problem, some of the informations are given to us, like say factored moment. Okay, based on the normal loading, what is the factored moment, or otherwise load will be given to us, span will be given to us, and we can find out what is the factored moment. So, it is given to us directly, that value is given to us 200 kilonewton meter. Say we have the torsional moment also. So, this Tu is given to us 50 kilonewton meter. Okay. Otherwise, the load will be given to us, and then distance will be given to us from the center of the beam, and we can find out the torsional moments. Okay. Force into distance, and then say the factored shear force is given to us. We know how to calculate all these things. Okay. So, it is given 100 kilonewton. In addition that, what we need? We need the concrete property and steel property. Concrete is given M20 and steel is given Fe415 steel. Okay. These are the information available to us. Now, problem is we have to design the reinforcement, design this section. How to design the section? We have to check all the requirements. Okay. First of all, we have to check what is the equivalent shear. Okay. Equivalent shear, we know that equivalent shear BE is equal to BE plus 1.6 then Tu divided by B. Okay. So, what is Bu given in the problem? Bu given in the problem is 100 kilonewton plus 1.6. How much Tu given? 50 kilonewton meter. Remember the unit. Okay. And B is given how much? B is given 400 mm. 400 mm. So, what you have to do? Either one of has to, you have to convert the same unit. Say if I write here in millimeter, then I have to multiply it by 1000. Right. Now, if you do the calculation, you will get the equivalent shear, and here it is coming, equivalent shear is coming 300 kilonewton. Okay. Just check this calculation. Okay. So, what I can do, this 0 0, this 0 0 get cancel. So, 4 if you cancel it, how much you are getting? 0.4. Okay. 50 into 4 is how much? 200 point. So, it is 20. 20 into 10 is how much? 200. 200 plus 100, it is 300. So, this is very accurate calculation. Next, we need to know what is the shear stress, torsional stress, tau B is. Tau B is what is that? That is B divided by B into D. B is 300 kilonewton. So, 300 into 10 to the power 3. I have converted into Newton, divided by what is BD? What is B is here given? B is given 400 mm and d is given how much? Here d means we need small d is how much given? 650. So Newton per millimeter square will get in terms of MPa. How much we are getting? 1.54 MPa. Okay, this is the tau BE. Now we have to check this tau BE with the maximum tau C max. Okay, so if you go to the code book, you will find tau C max for M20 grade of concrete. What is that value? That value is given in the code book in table number 20, that is given 2.8 MPa. So what we got, tau B is less than tau C max, so that is accepted. First of all, it is okay. Now we have to compare this tau B with what? With tau C. Now how to calculate tau C? To calculate the tau C, we need to know the percentage of reinforcement. Since we do not know initially what is the percentage of reinforcement, so we have to do some kind of assumption. Let us assume that the percentage of reinforcement here is 0.5. We will start with 0.5% reinforcements. Okay, so for percentage of reinforcement 0.5, if we refer to the table number 19, and table number 19, the value of tau C we can calculate as 0.48. Okay, that means what we can say, that tau C is less than tau BE, which is less than tau C max. Okay, so this is, first of all, both should be less than tau C max, so it is satisfying. Second one, it is saying tau C is less than tau B. It means what? We need to provide the shear reinforcement. Okay, so both longitudinal and transverse reinforcement for torsion is to be provided. If tau C is more than tau B, then you don't need to provide shear reinforcements. Okay, now for the design purpose, we will go to the next clause. According to the next clause, we will design it. What is the next clause written? First of all, we have to check for longitudinal reinforcement. What is that longitudinal reinforcement? Longitudinal reinforcement, if you remember that I have discussed now, ME1 is equal to MU plus MT, right? MU1 is equal to MU plus MT. Now we have to see that what is the equations and how we can calculate. MU is given to us. What is that given? MU is given to us how much? If you just see the problem, go to the next page. MU is given to us 200 kilonewton meter, right? MU is given to us 200 kilonewton meter. What is MT? Then we have to calculate. Let us calculate this MT here separately. What is that? This MT is equal to, what are the equation? TU divided by 1.7, then multiplied by, what was that? 1 plus d by b. Where is that? 1 plus d by b. Yeah, 1.7 I have written. So you put the values in our problem. TU, how much TU? TU is given 50 divided by 1.7 into 1 plus, what is D? D is here 700 in our problem, and what is B? B is 400. Okay, do this calculation. This comes out around 80.88 kilonewton meter. So one thing I can say from here, that what is that? That MT is less than MU. So, you don't need to provide compression reinforcement. Compression reinforcement is not required. Compression reinforcement is not required. Shortcut I have written. Okay. So, that means ME2 calculation is not required. So, ME1 is equal to 200 plus 88.88. That gives us how much? 288.88. So, now ME1 is known to us. Now, what we have to do? We have to calculate the longitudinal reinforcement for this ME1. Okay, we know how to calculate that. Okay, we will go to the next page and we will try to calculate that part. AS, area of the steel, divided by BD is equal to 0.85 divided by Fy. Okay. So, in that case, what is AS? AS equal to 0.85 into 400 into 650 divided by our Fy is 415. So, if you do this calculation gives me a value of area of the steel. We can find this value in terms of percentage also. Okay, so it's, or as in this way also you can find out, or if you want to find out, you can find out in terms of percentage also. Then this will give you the minimum area of the steel required. This value is coming around 532. Okay, 532.5 mm square. We are providing 1300 something, and this value coming 532. So whatever we have provided is satisfying. Okay, you can calculate this value in terms of percentage also. If we calculate it, this value is coming out to be 0.205. Okay, so this value is coming out 0.205. PT minimum is coming out 0.205. What should be the PT max? Maximum is given as 4% of the BD, but whatever we are providing is how much? Around 0.52 something. So, okay, which is, that means whatever we are providing is within the limit. Our percentage was 0.53, but minimum required is 0.205 and maximum required is 4%. So, whatever we are providing is 100% correct. There is no issue with the longitudinal reinforcements. Okay. Now, already I told you that since MT is coming less than MU, so we don't need to provide any kind of compression reinforcement. If MT is more than MU, then we have to calculate ME2, and for that we have to provide the compression reinforcement. Since it is not required in this problem, so we are safe for that particular size. Okay. Next we will see side face reinforcement, because since if you just recall those points, I said that when the depth is more than 450 of the beam, then we have to provide the side face reinforcement. Now, how to provide the side face reinforcements? Okay, that means when, let us see the next point, side face reinforcement. Side face reinforcements are provided when the side is greater than or equal to say 450 mm. Okay, so that is to be provided the minimum of 0.1% of the cross sectional area. Okay, total area required is 0.1% of the cross sectional area. Okay, so let us see what is that value, 0.1% of the cross sectional area. So here wave area is basically 400 by 700, because our section is how much? 400, this direction 400 and this direction 700. Okay, by mistake I have written 300. So how much this is coming? This is coming 280 mm square. Okay, so what was the guideline? Guideline was, I'll just read the guidelines how to provide that reinforcement. The face reinforcement with an area not less than 0.1% of the wave area. These bars are to be distributed equally on the two faces at spacing not exceeding 300 mm. So this value is coming 280 mm. So 280 mm for both face. So what is the value in one face? In one face we have to provide at least 140 mm square. So if I provide 10 mm dia bar, what is the area of a 10 mm dia bar? Say both side I have to provide this, so we can calculate what is the area of a 10 mm dia bar. Okay, just give me a minute. Okay, so area of a 10 mm dia bar comes 78. So if we provide 78, that is not enough. So because one side we have to provide at least 140. So how much we have to take? Say if I change this, let us take another into. So around 14 mm dia bar we can provide. Okay, so around, if we provide two numbers of 14 dia bar on both face, one each on the face, then it will be enough. Okay, it is coming, this area is coming more than 280 mm. Okay, so we provide two numbers of 14 dia bar on the at the middle steps. Okay, so this is one part, that how to provide the middle step reinforcement. Next we will go for transverse reinforcement. Okay, next part is transverse reinforcement. So for transverse reinforcement, before that we have to calculate those different component, that is B1, D1 and all those things. Okay. So, there are some components are there, something is called B1 and then another is there, that is called D1. What are those B1 and D1? B1 and D1 are basically the center to center distance. Okay. If I say that in longitudinal direction just 700 and at the top edge, because if you just look at this figure, I said this value was how much? 700. We are providing here a reinforcement, okay, and this gap is around 50 because that side we said 650. Similarly, whenever we will provide some minimum reinforcement here, this gap will also be 50. So, that is why center to center means we have to deduct here 50 also, here also 50. So, D1 will be how much? 600. Similarly, in this case also 400, this side it will be 400 minus 50 minus 50. So, 400 minus 50 minus 50, if we deduct, that value comes out how much? B1 is 300. Okay. Approximately we are taking, we are not taking the exact value. Then what is the equation given in the code book for calculation of the ASB? Okay. So, equation is ASB is equal to TUSB divided by B1 D1 into 0.87 Fy plus BUSB divided by 2.5 D1 into 0.87 Fy. Okay, this is the equation, and again there is a condition given that ASB shall not be less than tau B minus tau C into BSB divided by 0.87 Fy. Okay. So, this is the condition. Now, somewhere we have to calculate it. Okay. How do we calculate it? Let us see. So, what I am doing, rather than writing this, I am doing it in a other way. Other way is what I am writing here. I am writing here ASB into 0.87 Fy. I can take this side divided by say SB. SB is not known to us. So, this should not be less than how much? What was the tau B? Tau B was 1.154 minus what was tau C? We have used here, it was 0.48, right, multiplied by B. What is the B here? B here is 400. That means this value must be greater than or equal to 269.6. Okay, I am not writing here unit we have to see. This value must be greater than of this. Okay. Now, if I use the values here, from here also what I can do, I can take 0.87 Fy, 0.87 Fy common, and I can take it this side, and similarly SB also I can take it this side. So, it will be the similar equation, means here I have written ASB into 0.87 Fy divided by SB. Same thing I can write for that equation also, ASB into 0.87 Fy divided by SB. Okay. ASB into this equal to what is there? TU divided by B1 D1. What is TU? Okay, let me write the equation. TU divided by B1 D1 plus BU divided by 22.5 D1. Okay. What was the TU in our problem? In our problem, TU was 80. What was that? 88.88. Just let me check that. TU, BU is this. TU was given, sorry, TU was given 50. Okay, it was given 50. So, this value will be, this value was given 50. Just now we have calculated B1. Okay, B1 was how much? 300. D1 was how much? 600 plus BU. BU is already given in the problem, and what was that value? BU was 100. right, 100 divided by 2.5 and D1 was just calculated we have 600. Now you calculate this value and check how much you are getting here. Okay, remember these values are given in kilonewton, so I am writing in terms of Newton, this I am writing in terms of Newton. This is kilonewton millimeter, so Newton millimeter, okay, 10 to the power 6. So if I get cancelled, this will be Newton divided by millimeter, this will also give me a Newton by millimeter. Okay, I will calculate and I will come back quickly. Okay, so I have done the calculation. This value is coming 344.45 Newton per millimeter. So we need a minimum of this value, how much? 344.45. If you see the previous what we did, as per the condition that this value must be greater than or equal to 269.6. That means whatever we have calculated here, we can say is correct. Okay, that means what I have written, ASB into 0.87 Fy divided by SB is equal to 344.45. 344.45 is accepted. So from here I can calculate SB. What will be the SB? SB, if I take this side, it is ASB. Now we have to assume something. Okay, so 0.87 into 415 into ASB divided by 344 point how much 45. Let us assume that we are using 2 lakh 10 dia bar, so 2 into pi by 4 into 10 square. Okay, what we are using? We are using 2 lakh 10 dia bar. So if you do this calculation, it will give you the spacing. So this value comes out 164.65 mm. Okay, now we have to check the guideline that what should be the maximum spacing. Okay, what is the maximum spacing guidelines? It was given, if you check that part, the maximum spacing should be equal to x1 or x1 plus y1 by 4 or 300 mm. Out of this, whichever is the minimum. Here what is the value of x1? What is the value of x1 that we have to calculate? How to calculate that? If you just recall the figure or otherwise, quickly I am drawing the figure now. Whatever I did, from there I can get the value of calculation of x1 easily. Okay, so our beam is this. Here we are providing the main reinforcement, then we are providing the transverse reinforcement like that. Okay, so if you just go back to your slides, then you will be knowing what is x1. x1 is basically the center to center distance from the transverse reinforcement. From the transverse reinforcement, what is the center to center distance? That is basically called the x1. Okay, so how to calculate that? Let us see. Let us see that our overall B was how much? 400. Okay, this I have assumed, this from center to this value I have assumed as 50. So if this was 50, then what is this value? Okay, so this was 50 minus, what is the main reinforcement that we are using? We are using main reinforcement as 25 dia. So this is 25 by 2 minus transverse reinforcement, we are saying how much? 10 mm. So 10 by 2. So what I have written here, you just check. I have written 50 from here to the center, then I have written half of the main reinforcement diameter and then half of the transverse reinforcement diameter. Then I will get from the center of the transverse reinforcement to up to this, what is this distance? This distance I have to deduct from here. So this distance will be how many times? This distance I have to multiply it by 2 times, this side also and this side also. So now check how much this value. So this value comes out like that. How much? 100 minus 25 minus 10 is this 65. So 400 minus 65 is how much? 400 minus 65 is coming 335 mm. Similarly, we can calculate for y1 also. What will be that y1 will be 700 minus 2 side 50 minus 25 by 2 minus 10 by 2, okay, because this is also from the center of this transverse reinforcement to the center, here the transverse reinforcement, okay, it is like this, so center. So this will be the similar process. How much this is? This is 100 minus 25 minus 10 is how much? I said 65. So 700 minus 65 is how much? 635. Okay, so we got these two values as one is 635 and another one is this. So now we have to see this. X1 means what? That is 335. Second one will be 335 plus 635 whole divided by 4 or 300 mm. So what is this value? This is coming 970. 970 by 4 is around how much? 200. 970 divided by 242.5. So it indicates that the spacing cannot be more than 242.5. okay. What is the spacing we got? We got, if you see the backspace, how much? 164.65. so we will provide 160. Sorry. So ultimately what we can say, provide 2-legged 10 dia vertical stirrups at the rate of 160 mm center to center. So just in a summary, what I did in the problem was given to us. First we have calculated the longitudinal reinforcement. What longitudinal reinforcement we are providing? We are providing 2 number of 25 dia plus 2 number of 16 dia. Then I have checked whether I need to provide compression reinforcement or not, that is MT. If MT is more than ME, I have seen it is not there, so it is not required. Then I have go for calculation of the transverse reinforcement. To calculate the transverse reinforcement, I have calculated D1 and B1. What is D1? D1 is the center to center distance of the longitudinal reinforcement, and B1 is also the center to center distance of the longitudinal reinforcement, but B1 is in transverse direction and D1 is in the other directions. Okay. Then I have calculated the SB. How we have calculated? I have used the minimum reinforcement criteria. I am just going back and I will show you what I did here. I have checked what is the minimum criteria. Minimum criteria was this. So this much minimum area is to be provided. So I have taken this constant and this side, and I have said that this value must be greater than this value. So how I got this value? I have used the original equation and I have taken this separately and I have calculated this value, and this value came out that 344.45. So this is more than 269.6. That means whatever the calculation we have done is correct. B1, D1 and all those things is correct. So based on that I have written them. Then I have assumed that 2-legged 10 dia bars we are providing. So 2-legged 10 dia bars we are providing. So what is their area? That area I have used and I have calculated the spacing, that minimum as per this calculation 164.6 spacing is required. Now what is the maximum spacing? Maximum spacing is x1 or x1 plus y1 by 4 or 300 mm, whichever is minimum. Then I have calculated x1. x1 is the center to center distance of the transverse reinforcement along the width, and y1 is the center to center distance of the transverse reinforcement along the depth. So that I have calculated here x1 and then I have calculated y1. So this is x1, then x1 plus y1 by 4 is this value and this is 300. So which one is maximum here? 242.5. That means our spacing must be less than 244.5. Our spacing came how much? 164. So we are providing a spacing of 160. Okay. So this is the transverse reinforcement and this is the longitudinal reinforcement. In addition to that, what we said, we are also providing 2 number of 14 dia reinforcement at the side face. Okay. So finally you draw it whatever you have done here. So this is the original beam. Okay, and that original beam you provide the reinforcement. Reinforcement I am providing here. I am providing here. I will show this reinforcement with a separate color here. So these are the center and these are the, okay. Then I have provided here at the center one and then center one. Then what I did, I need to provide this shear reinforcement that I have calculated. Okay, so shear reinforcement was this was the shear reinforcement required. What was the shear reinforcement? 2-legged 10 dia at the rate of 160 center to center. The side face reinforcement was, what was that? 2 number of 14 dia on side face, okay, and this was 2 number of 25 dia plus 2 number of, what was that? 16 dia. These are torque reinforcement, deformed bar. So, you can use the symbol T, okay, everywhere you can use the symbol T, okay, and this is some minimum reinforcement that we have provided, because we do not need to calculate it, okay. So, some kind of minimum, say 10 dia or 12 dia, 2 number of 10 or 12 dia torque bar we have provided. So, this is what is the design, okay. So, in this design we have considered the torsional moments, okay. Like that you take more problem and do some practice on that, and if you have any issue you can connect with me, okay. So, next we will come with a different problems, okay. That is it for today.